Hi, welcome to section 6.1 of chapter 6 lecture. So in this section, we are going to talk about the octet rule as our main topic. And also I'm going to discuss topics called multiple bonds between atoms and how the multiple bonds are going to affect the bond length of the atoms or molecules that we are going to study. So before we jump on to discussing what is an octet rule is, again, I cannot stress this enough and the importance of Lewis dot symbols for us to understand what is an octet rule is and how to draw chemical structures are. That's why I included this slide again here so that we just revisit just before we really need it. Lewis dot symbols explains what are the valence electrons for each element and how those valence electrons are available for bonding. What electrons are available for bonding is the single electrons are available for bonding. So group 1 has one single electron and a group 2 has two electrons. They just follow the group number as you see here, the trend. And similarly, group 3 electrons had three single electrons. And similarly, group 4 electrons had four single electrons in them. There is a trend. If you know about one group, you can comment on every element in that group. And a group 5 is different from group 4 as it had a lone pair. It is the first element that has a lone pair when you look at the across the periodic table. So does every element in the group 5. They all have one lone pair and three single electrons. What it tells is any element from group 5 can have a lone pair and can make three bonds. And group 6 elements like oxygen or sulfur or selenium, these elements have two lone pairs and two single electrons. You see two single electrons on two sides and two lone pairs. Doesn't matter where you put them, but you just need to remember that they have two lone pairs and two single electrons. And group 7 had three lone pairs and one single electron. And it is true for all the elements in group 7. Okay, so they are, all elements which are, unstable on its own will make bonds with another elements or same elements of its own to make molecules. And what is the driving force for these elements or atoms to make the molecules is to achieve stability, achieve noble gas electronic configuration. How are they going to achieve is by following the octet rule. That is why we need to know what is an octet rule is. We are going to learn if any of these elements or all of these elements are going to achieve the stability of the noble gas electronic configuration by having the 8 valence electrons on its shell, which are a replica or the identity of the noble gas electronic configuration. As you see here, noble gases has 8 electrons and all of them are lone pair of electrons. Obviously helium is an exception, so just okay with that, right? It is a noble gas, but it doesn't fit in a larger group of electrons that has 4 lone pairs of electrons. Okay, so this is going to be our goal, is to find total of 4 lone pairs or 4 pairs of electrons to have the 8 electrons total. So we are going to learn octet rule now. So this is the octet rule. This is how it is defined as. According to octet rule, an atom will gain or lose or share electrons in order to achieve the noble gas electronic configuration, because that's where the stability is for the atom is. So an atom will try to make bonds or will try to gain electrons or will try to lose electrons to achieve the noble gas configuration. I'm not going to go over the examples of losing electrons and gaining electrons because that's what ions do. When you have a ionic bond between a metal and non-metal, metal lose electrons and non-metal gains electrons, and they achieve 8 electrons on its outer shell electron configuration. So that is how that is how they make bonds, ions. and then the ions combine in electrostatic attraction fashion to form an ionic bond. But we are not going to discuss that. In chapter 6 and 7 is exclusively for covalent bonds. So we are going to focus on shared electrons between nonmetals. So our goal is to, let me go back and show you where is our focus is. Our focus is on nonmetals. These are nonmetals, or maybe bismuth too, but I'm not sure. It's been a while since I looked at the metallite range, but those are the main nonmetals. We should maybe include, boron in it as well and hydrogen in it as well. So those are the nonmetals, at least metalloids, combination of nonmetals and metalloids. These elements are the elements that are not going to lose their electrons because, as we discussed previously, they like to gain electrons because they gain more stability if they gain electrons, as it's said by electron affinity value. So as a result, because they were not losing electrons and everyone wants to gain electrons, the only way to make everyone gain electrons is if you ask them to share electrons. And all of these electrons share electrons between them. And we are going to learn how they are going to share electrons and achieve the octet rule satisfied. Okay, let me just show you a small table, but very useful for the octet rule. And you can apply this to, again, for all elements in group 4, and you can apply this to all elements in group 5, and oxygen, and all elements in group 6, and halogens, all elements in group 7. So this is how they achieve the noble gas, they achieve the 8 electron configurations in its outer shell. So they form, well, hydrogen is an exception because it only had 1, so I'm not including that. This is where we are going to focus on, right? How carbon is going to achieve the octet rule is, remember from previous slide, carbon had 4 single electrons. So which means it can make 4 bonds. And if it makes 4 bonds, it is asking another element to give 1 electron each. So a bond is equal to 2 electrons. So as a result, it had 8 electrons total because 4 times 2 is 8. And nitrogen has a 3 single electrons, which means it can make 3 bonds. So 3 times 2, and it had 1 lone pair, so 2. That is how it is going to achieve 8 electrons. Oxygen had 2 single electrons, which means it has 4 electrons over there, and it had 2 lone pairs, which means 2 electrons each, total 8. So octet rule achieved. And halogen will only can make 1 bond, so there are 2 electrons in a bond, and it had 3 lone pairs, which means it had 6 electrons over there, so total of 8 electrons if it made 1 bond and has keep its own lone pairs. So this is the combination that you're going to look for when you start drawing Lewis structures. Do they have a total of 4 of any of these combinations? Now, sometimes it can change. Sometimes, nitrogen might end up with having 4 bonds. It is still fine. It doesn't necessarily need to have, 1 lone pair and 3 single bonds all the time. Our ultimate goal is to see if an atom is going to follow the octet rule or not. Octet rule only talks about having total 8 electrons in the form of shared electrons. It can be bonds or it can be lone pairs. Doesn't matter in what combination they were. So nitrogen, instead of having 3 bonds and a lone pair, it can have 4 single bonds. And oxygen, instead of having 2 lone pairs and 2 bonds, it can have 3 bonds and only 1 lone pair. It still follows the octet rule because it is still 8 electrons. And sometimes you're going to see halogens, especially chlorine, bromine, and iodine. These, which follows under exceptions that we are going to talk at the end of the chapter, they not necessarily going to have 1 bond and 3 lone pairs. They will have sometimes more than one bond and less number of lone pairs. Some of them will have like 3 bonds and 1 lone pair, or 2 bonds and 2 lone pairs. It is still fine because what we are looking for is not these fixed number of lone pairs and bond combination. We are looking for total of 8 electrons. It could be in the form of number of bonds or in the form of number of lone pairs, but together they should account for 4. So that 4 times 2 is 8. So octet rule is satisfied. So it is what we are going to look for throughout this chapter whenever we are going to check the octet rule for any element. Okay. Now let's dig into more details. So I'm going to use an example here to explain octet rule by taking an example. Let's discuss fluorine. So we already know that fluorine from group 7, so it should have 7 valence electrons. So how those 7 valence electrons are present is they were present in shell 2 in the form of 2s2 and 2p5. Again, if you have any doubts how we come up to these 3 lone pairs and 1 single bond, I can explain here. I'll take this opportunity and explain here. So 2s, 2p, right? So we have 1 orbital in 2s and 3 orbitals in 2p, right? Each orbital can take maximum of 2 electrons only. So we said 2s2 here. So I have 1 electron here, and because 2s is lower in energy level than 2p, I can start pairing 2s now. Okay, and 2p5. So according to Hopper rule, you need to equally distribute electrons first before you start pairing them. So I put 3 electrons currently, and I have 2 more electrons. So now I can start thinking about pairing an electron. So do you see now that currently here I have a lone pair, a lone pair, a lone pair, and single electron here. This is how we end up having 3 single lone pairs and 1 single dot for fluorine, because that is how they arrange themselves in an orbital. Why a lone pair is important is lone pair tells us that there is no more room in that particular orbital. What is the significance of the single bond is it tells us that there is a room for 1 more electron. And how it is going to accommodate that by is sharing this lone pair, this single electron with another atom single electron and making a bond. Okay. Now let's see how fluorine, now which currently had only 7 electrons, is going to achieve the octet rule through sharing of electrons, right? Because as I said, these nonmetals are not going to lose or gain electrons, they only share electrons. So let's focus on that, how fluorine is going to share electrons with another element. I want to take an example of fluorine making a molecule with another fluorine. So let's take another fluorine molecule. So we have 2 fluorine atoms with 7 electrons each. Currently, they were not stable by themselves because they don't have octet rule followed. They don't have 8 electrons in its valence shell, the outermost shell. So how are they going to achieve is by sharing electrons between them. So the red fluorine talks to blue fluorine. Hey, you want to help each other out, and so that we can feel total 8 electrons in our valence shell. So naturally they agree because it brings the stability to the overall atom. So these individual atoms are unstable compared to this fluorine molecule. So why it is more stable is here each fluorine is going to feel the electron cloud of all the electrons it is exposed to. So here the fluorine on the left is exposed to obviously 2 electrons here, 2 more electrons here, 2 more electrons here, and it is already connected to 1 electron, right? So there are total 7 electrons here. So how it is going to feel 8 electrons is because it is sharing its electron with another element. The another fluorine is sharing its electron, it is in its vicinity. So that electron is shared by this fluorine. So this fluorine is exposed to a total of 8 electrons. Some of them are its own, some of them are coming from another element. Still fine because it is still in its outer shell. So what we are looking for is having 8 electrons in its outer shell. That is how it is going to achieve the total 8 electrons. And let's look for another element also. So this element currently here had 2 electrons here, 2 electrons here, 2 more electrons, so 4 electrons in its valence shell, 2 more electrons here, so total of 6. And it already had its one electron here, so total 7 electrons. Because it is making a bond with another element by sharing its single electron, the another element single electron is also in its vicinity. Now the other fluorine element is also going to experience 8 electrons in its vicinity. This is the reason why atoms makes bonds, because they can make up for their self deficiencies of having low number of electrons by sharing electrons with another atom. This is the main driving force behind atoms forming molecules. Because here now each of the fluorine is almost acting like the neon, the atom with 8 valence electrons. So neon has, if you guys can recollect, has the electron configuration of 1s2, 2s2, 2p6. There are 8 valence electrons in shell 2, which is what the noble gas electronic configuration. That is more stable because noble gases are stable because they have complete shell. So because the noble gases have 8 electrons and rest of the elements are trying to copy it because that's where the stability is, because they were not exposed to any other element, because they don't have any more spaces to react with another element. That's why they are trying to achieve that 8 electrons, and fluorine achieves that by forming a single bond. Okay, there are multiple ways, but fluorine achieves that by forming a single bond because it already comes with 7 electrons of its own. It just needs one more, and it gains that if it forms one more bond. Okay, even though we are spending a lot more time here because this is really necessary for you to master. That's why I'm spending a lot of time here. Once you get the hang of this one, we can move through the things so quickly. That's why I want to take this slow and explain. If you get it, you can move on faster. But there are some students that needs time in absorbing this content. That's why I'm spending lots of time here and re-explaining because I need everyone to be on the board on this topic so that we all can get along when we discuss the bigger complex topics. Okay. Let's discuss or dig deep into what are these octet rule is. We already said that valence electrons are the ones that are used to make bonding with another elements, and atoms also has its lone pairs that to be counted towards the octet rule. So we already used this example to explain how atoms will share electrons, and here we said that fluorine is making single bond with another element by sharing its 2 electrons, and the way let me use another color. The way we know that they were making a bond is, because it looks difficult to write these dots, pretty soon we are going to replace those dots between elements to a single line. Each line is going to represent 2 electrons, and we call them as bonds or shared electrons. And you have to require to show these lone pairs, whichever element has lone pairs, but you don't really require to show how many electrons in a bond, because it is pretty straightforward that whenever you replace 2 electrons with a bond, that's common. You can decode whenever you see a single bond, oh, there are 2 electrons. If you see more than 1 bond, or more than 2 electrons present. So you just require to show the lone pairs, but not the bonded electrons. That's why we are going to replace them with a line. Okay. But I need you to still show the lone pairs that are present. Lone pairs are the electrons that atom has, and the bonded electrons are the electrons that are present in between the atoms. Okay. So now that we know what is an octet rule is, we are going to slowly move towards a Lewis structure. Okay. So what is a Lewis structure? I'm not going to fully discuss Lewis structure here. Section 6.3 is where we completely going to focus on Lewis structure. Here we are going to discuss basics of Lewis structure. And we are just going to introduce ourselves what is the Lewis structure is. Lewis structure is a representation of covalent bonding. What is a covalent bond is when atoms share electrons to make a molecule. We call those types of bonding or shared pattern as covalent bonding. Okay. So here are a couple types of way a atom makes bond with another atom. I'm just going to review them. So one type is by sharing electrons. Shared electron pairs are shown as in the form of dots or line, as we discussed in the previous slide. And lone pairs, you don't have to convert to anything else, because lone pairs we kind of want to see them because they kind of matter when you talk about reactivity. It helps us to quickly read the scene of what is going on there in a chemical reaction. That's why we kind of chemistry, we keep the lone pairs on the atom, but we don't show the bonding electrons because it's kind of distracting. It's kind of like it takes our focus away from lone pairs. That's why we replace all the bonding electrons with a single, with single line or multiple line if it is required, if there are more electrons, and we keep the lone pairs intact. Okay. So in this molecule, again, here you can see that oxygen is having total 8 electrons. Oxygen already had 2 lone pairs of its own and a single electron of its own, and it shared those single electrons with each hydrogen on both sides, which helps the oxygen to have a total of 8 electrons. So oxygen is following Octet rule by making 2 bonds with other elements. In this case, it is hydrogen. In another case, it could be another oxygen or another element. It doesn't matter which element it is. It has to be another non-metal. As long as it is another non-metal, it is good to share the electrons with it. Okay. So now we are going to shift our focus on multiple bonds. It's kind of like we talk about it and we move on from it. Here I'm going to show you the chemical structures that you quite don't know how to draw yet, but I kind of have to show it now because we are going to go in different directions. So when you see structures, just trust that I'm showing you something that is correct. Okay, I'm not misleading you. So when you draw Lewis structures, there is a possibility that an atom will make, I have a couple models here, I can use them now. An atom can make or can share electrons with another atom through a single bond. This is what single bond is. Or another possibility is an atom can make bonding with another atom through multiple bond. Here you see, this is, imagine this is a carbon, this is another carbon. These 2 carbons here are having multiple bonds between them. It is because they shared their electrons twice. Carbon first decide to make 1 bond by sharing 1 electron each, and then it decide to share 1 more electron each. That is how we have double bond. And also you can have triple bond as well. I just don't have model for it, but you see 1 more bond between atoms. So here we are going to discuss those multiple bonds, even though you don't know how to quite draw them yet. So when you share a pair of electrons between them, what you have is a single bond between them. This is what we call a single bond. Okay. In a double bond, which is a form of multiple bond, atoms share 2 pairs of electrons. They share 2 pairs of electrons, which is important. 2 pairs of electrons. Here is a great example of that. A carbon here in the center is sharing 1 pair and 2 pairs with the oxygen on the left. And also carbon in the center is sharing 1 pair and 2 pairs with the oxygen on the right. Because it is sharing 2 pairs with the same element, we are writing double bonds here. That is why we are writing multiple bond, and we can call it as a double bond. Okay. And again, if you see here, or pay attention from now on, whenever a main group elements like main group non-metals make a bond, they always have 8 electrons. See, carbon in the center has 8 electrons if you count, excuse me, There are 8 electrons if you see there. 4 on the left side, 4 on the right side. Let me erase the ink and show you the 8 electrons present on the oxygen on the left here. In here, you see 4 electrons here, 2 more here, 2 more here, 8 electrons. Also the oxygen on the right, 4 electrons that are shared with the carbon, 2 electrons in the form of lone pair, another set of 2 electrons, total 8. So each element has 8 electrons, which is a must. So it does have it, which is good news. So it is a correctly structured. If any structure did not have 8 electrons, something is wrong. We need to talk more about it. So a triple bond occurs when atoms are held together by 3 electron pairs. So 3 electron pairs. An example is a nitrogen sharing 3 electron pairs with another nitrogen. Here you see 3 electron pairs. Okay? If you see an opposite, let me rewrite another style. Maybe that makes more sense. Like nitrogen, 1 pair, another pair, another pair. This makes more sense than the one that currently shown there. So those 3 lone pairs, or those 3 shared electron pairs, are leading to make 1, 2, 3 bonds between nitrogen. That's why we call it as triple bond. Now, if you count again, each nitrogen has 8 electrons on its vicinity, 2 in the form of lone pair and 3 shared bonds means 6 electrons, total 8. And also this nitrogen on the right also had a lone pair and it is still connected to 3 bonds, so total 8 electrons. That is how they were achieving the 8 electrons, the octet rule. We kind of say that as they were satisfying the octet rule. Okay. Now that we know what our multiple bonds are, let's focus on the relationship between multiple bonds and the bond length. All right. So what is a bond length is? Bond length is defined as the distance between the nuclei of one atom with the another atom that they were making a bond with or sharing the electrons with. Okay. So there has to be some logical reasoning with the multiple bonds and bond lengths. And now we are going to see what it is and why it is like that. Okay. Here, if you guys can see, here I included this GIF image to explain the difference between single bond and a multiple bonds. Imagine, having 2 rubber tennis balls and tie each one of them with just 1 rubber band, a single strand. And if you try to pull it away, it is so easy to pull it away because, they're only connected ones, loosely tied, right? We can say so easy to pull it back. You can say that they are going to have, longer bond length because there is no need for them to stay really close. Whereas if you tie each ball with the 3 strands of rubber bands with the same other tennis ball, and if you try to pull them together, it's so hard because they were tied together multiple times and it is so hard to pull them apart. They kind of had to stay close to each other because there are so many factors involving tying 3 times this ball with tying 3 times another ball, which kind of, really cool daily life example to discuss the effect of multiple bonds on bond length. So according to that, take-home experiment, you can predict that single bonds are going to have a large bond lengths between the atoms that were making the covalent bond, and the multiple bonds making atoms will have a shorter bond length. Here we have the proof to prove that. Here you can see that I'm going to highlight the examples that has the bond between same atoms multiple times. So CO, excuse me. Here, CO is comparable to C double bond O and C triple bond O. Same atoms, so should have same atomic size, but only difference between them is one has more bonds than another. So as you increase number of bonds, the bond length is decreasing, right? It is decreasing from CO to C double bond O to C triple bond O. And here you can see the same trend for CC to C double bond to C triple bond C. Bond length is decreasing while number of bonds are increasing. And also you can see the same trend between CN, C triple bond N, C double bond N, C triple bond N. It is decreasing. Again, you can see the same trend in NN, N double bond N, and N triple bond N because bond length is decreasing. You can see the same style in N single bond and N double bond O, and oxygen-oxygen single bond and oxygen-oxygen double bond. Again, you don't need to remember those numbers. You need to know the trend. You need to know the trend that multiple bonds are shorter in bond length than the single bonds when you have the bond between same elements. Here, I just have some data for you. What we just discussed in the previous slide. It's kind of redundant, but I just want to highlight again. Here you can clearly see that NN single bond is larger than NN triple bond, and NN triple double bond is larger than NN triple bond. Okay, so it is the logical explanation or logical link between multiple bonds and bond length. Here is the last slide I have from this section here. So the numbers that you see here, it is the bond length, right? Bond length again has the relationship with the bond energy that I'm not going to discuss now because we are going to spend lots of time on bond energy in chapter 10. So bond length and bond energy kind of work opposite. So if you have a shorter bond length, it would have a greater energy. And what is a bond energy is, again, you don't need to know any of this now. I'm just giving you a heads up what you have to expect in future, because everything is related in chemistry. Bond energy is the energy required to break the bond. And if you have single bond, it is easier to break it compared to if you have double bond or triple bond. So as the number of bonds increasing, bond energy also increases, which we are going to again discuss that in chapter 10. That's all for this topic. I'll see you again in section 2.2 of this chapter.